everyone. Welcome to Astronomy on Tap and the Triangle. This is our last event in the year, and we are very excited to have you here. And we're especially happy to be joined with Professor Robert Jannsens. And we're going to get started today with a little game that some of you might remember from our early events when J.J. Hermes was still organizing our events. And he played a game called Reagan versus Sagan. So we're going to jump right in and we're going to do a spin on that today. So let me share my screen. We'll get started. All right, so our spin for today is Bill versus Neil. So we have Bill Clinton, US President, versus Neil deGrasse Tyson, Director of the Hayden Planetarium. So we've got 3 quotes we're going to go through, and you can vote and see who do you think said it. And we'll go ahead and start with this first quote. Nobody's right all the time, and a broken clock is right twice a day. We're compelled to spend our fleeting lives between these two extremes, knowing we're never going to be right all the time and hoping we're right more than twice a day. And if you go to slido.com, slido.com, and put in the code G368, you can actually join this poll and put in your response in real time so we can see what everyone responded. So I'll give you all a minute to pull it up. Robert, you should also feel free to participate if you're interested.
I don't want to jinx the computer here.
Give it a couple extra minutes in case anyone wants to get on. All right, well, it looks like we have 6 people responded, so we can go ahead and look at the answer for the first question. And it looks like we have a 50-50 split. So, and the right answer for this one was Bill Clinton. So kudos to those of you who got it right, and the rest of you, maybe we'll have better luck on the next question. The next quote is, the most successful people in life recognize that in life they create their own love, they manufacture their own meaning, and they generate their own motivation. Is that Neil or Bill? Take a minute and vote on that. was actually quite interesting trying to come up for quotes to put in this, because I think when JJ did this with Reagan versus Sagan, I think Ronald Reagan may have actually had more astronomy-related quotes than Bill Clinton did. It seemed that in the Clinton era, the main scientific project was the Human Genome Project.
Yes.
So I think I found a lot more quotes about that than I did about astronomy.
Yeah, I can believe that. Yeah, that was actually very big at that time, and a very successful project too.
All right, we've got a seventh person now. Let's give it a minute longer in case anyone else is gonna dial in the poll.
I see number 9 now.
Mm-hmm. It's good to have y'all come on and participate. Let's go ahead and check out the answer for this one. All right, so actually, so this one was Neil deGrasse Tyson, and it looks like the majority of you got this wrong. So a little bit of surprise there, and we can go ahead and check out the third quote. So the third quote is that we cannot idealize technology. Technology is only and always the reflection of our own imagination, and its uses must be conditioned by our own values. What do you think, Bill or Neil? Okay, we have a 10th person now. Let's give it just a second longer.
Can you see how many people are on?
Not at the moment because of my screen share.
Oh yeah, of course.
But yeah, in the YouTube studio, you can see how many people are on, and you can interact with comments and stuff, which is pretty cool.
Which is cool, yeah.
All right, let's go ahead and check out the answer for this one. See what you guys thought. All right, so we have another 50-50 split. Seems like y'all are pretty divided tonight, but this was a Bill Clinton quote. So hope that was fun. Thanks all for participating in it. And I'm going to do a little bit of an intro talk, and then we'll get into our main lecture. So thanks again, everyone, for coming out. Again, this is our last event of the year, and we're really excited to have you here. We're not going to be having an event next month as usual, because during January, this semester is not in, and a lot of people are traveling and stuff, so it's just easier to wait until February. So we will see you in February, I think the 2nd, for our next event. But tonight we're going nuclear, and I want to start off just thinking back to the early days of astronomy. So back in the days of Galileo and Kepler, astronomers used pretty rudimentary telescopes by today's standards, and they looked through them at night at solar system objects, nearby stars, and they drew what they saw on paper, and that was the best that they could do at the time. The telescope was just invented, and even as limiting as that sounds, they made a lot of major discoveries that way, related to the laws of planetary motion and related to our place in our own solar system, regarding, the heliocentric model, the sphericalness of the moon, and all those sorts of things, which is pretty cool. Today, technology has advanced a lot more, but what hasn't changed is that there's still basically 5 observables in astronomy. Astronomy is not like um, other fields like chemistry or something like that, where you can go into a lab and you can measure something about a star specifically with a thermometer, right? There's basically 5 things in astronomy that we can measure. We can measure the position of a star or galaxy or planet, we can measure where it is on the sky. 2, we can measure its brightness, so how bright it looks to us relative to, um, the sun or some other reference object. We can measure the color of the object. So you can see, a blue star is more hot than a red star. So it's a color is an indication of temperature. We can measure the polarization, which I won't get into, but it's basically the orientation of the incoming radiation. And we can measure that, which is important for understanding, um, for example, the magnetic fields in the galaxy. And then the 5th thing we can measure is time. So that really helps us decode complex signals. So you could have a star, for example, that um, the brightness, so number 2, could be changing in time as it's growing, shrinking, pulsating. Just be one example of that. And I want to dive a little deeper on color. So in our day-to-day lives, color is something we interact with all the time: red, blue, green, yellow. Um, but in astronomy, color has a much deeper meaning. And you may remember from your high school physics or chemistry days the electromagnetic spectrum, which I have in this picture on the right. And color in astronomy means much more than these colors that we see in our everyday life. It means the radiation that we can see at every wavelength, from radio waves to infrared, ultraviolet, the light that we can see with our eyes, and then high energy radiation, X-rays and gamma rays, some of that you're going to hear about tonight. Um, and this multi-wavelength astronomy is a huge advancement over, if we think about the astronomers of Galileo and Kepler's time, of what we can understand using our instruments. And to sort of illustrate this concept of multi-messenger astronomy, multi-wavelength astronomy, here's a picture of the Crab Nebula. And it's actually 5 pictures, and each picture is taken with a different astronomical instrument. So the biggest one in the top right is an optical image. So if you had really good eyesight, this is an example of what you might see in the sky, if you could see the Crab Nebula. But around it, so for example, in the top left, you have radio and infrared, and in the bottom right, you have ultraviolet and X-ray. So each image is a picture of the same object with a different kind of radiation or color coming into it. And again, color in the sense of completely different types of radiation rather than just red versus blue. And if you study these, I would encourage you guys to do some reading about the Crab Nebula when the event is over, but you can find something different in every picture that helps tell you about what the story of the Crab Nebula is. And just one example of that is if you look in the bottom 2 pictures, remember this is very high energy radiation in those pictures, ultraviolet and X-ray. And you can see the actual pulsar at the center of the nebula, and you can't see that in the optical infrared due to dust that's there. So this idea of multi-wavelength, multi-messenger astronomy has been huge for what we can discover in the universe, because each of these pictures taken with different telescopes tells you a different aspect about the story of the Crab Nebula. And that applies everywhere, not just for the Crab Nebula, but in lots and lots of aspects of astronomy. Here's 2 examples of high energy telescopes. So on the left, picture of the NASA Fermi Gamma Ray Space Telescope. And on the right, we have the Chandra X-ray Observatory, which is also a space telescope. And so these are telescopes that are orbiting like satellites, and they're headquartered by NASA. And these are sort of some of the primary instruments that are used to do this multi-wavelength astronomy. And on the bottom, you can see 2 pictures that were taken with these instruments at these high energies of radiation. And with that, I want to come back to the observables in astronomy. So we talked about these 5 observables, but there's a little bit of a gotcha to this because in the past 2 years, we've had the advent of gravitational wave astronomy. So I think that was it was 2016, I think, that gravitational waves were discovered. So this is something that is completely pioneering a new era of astronomy, one in which we're not limited only to position, brightness, color, time, polarization, but we have something beyond just electromagnetic light that we can work with. So the questions that we're going to answer through LIGO, which is what you're seeing in the top 2 pictures, this facility called the LIGO, what we're going to answer by having this instrument is it's going to be tremendous over the next few years. So it's expanding what we have to 6 observables rather than just 5. And with this idea of multi-wavelength astronomy, not only with gravitational waves, but with our 5 observables and all these different kinds of instruments that we have that can be combined to provide information, astronomy is now spanning every order of magnitude from the walls, voids, and filaments that create the cosmological structure that are 10 million light years across, down to galaxies and molecular clouds that are 10 light years to 100,000 light years across, all the way down to nuclei, which is what you're going to hear about tonight. And nuclei are talking about 10 to the minus 15 meters. So that's a 1. It's like 0.00, 15 zeros, not a 1. It's extremely tiny. And what's beautiful about astronomy is that understanding these nuclei is key to understanding how everything else functions. So you have to understand the physics of these nuclei, of these chemical reactions, of these nuclear reactions to understand how, at a fundamental level, we can have stars that create galaxies and galaxies that cluster into the cosmic web that we see in the overarching structure of the universe. So I think it's pretty amazing that astronomy is spanning all these scales now that are so intimately connected in ways that are just kind of inconceivable to our intuition. And with that, I'm going to let Professor Robert Jannsens tell you some more about nuclei. He is the professor of nuclear physics at the University of North Carolina at Chapel Hill, and a strong leader at Tunnel, which is the Triangle University's nuclear laboratory. So with that, I'm going to give it over to Dr. Jannsens.
Okay. Let me try to see if I can share my screen. All right, Zach, I hope that this is visible for everybody.
I think we're good, thanks.
Okay, well, first of all, thank you, Zach, for the invitation. And I really hope that one of these days we can really have a real astronomy on tap, where we get to meet one another and talk more about all these things that excite us. Zach gave us a wonderful introduction here, showing that this science spans the distances that are incredible, from the largest scales of the universe all the way to the atom and the nucleus of the atom. And that's what we're going to try to talk about a little bit tonight. And I'm going to talk about it through an example, in particular, through an example of how we actually can detect nuclei through measuring gamma rays. And let me start with something that will probably surprise you a little bit. This is the announcement of a movie of 2003, one of the series of the Hulk movies that will probably surprise you. But it turns out that what the Hulk is holding here is actually a copy of a real detector called gamma sphere, which is still at the moment, but not for very much longer, the most powerful gamma ray spectrometer that we have on Earth. And we use this device to actually not to irradiate people. In fact, it doesn't. That's where the story goes wrong, of course, with the Hulk. And by the way, this was not a very good movie, in my opinion. But the Hulk gets radioactivity from this device, is the claim, while in fact what the device does is detect radioactivity. And if there are nuclear reactions in the stars, they're going to produce gamma rays. And if we can reproduce some of these gamma rays on Earth, then we will understand better what's happening in the stars. And that's the general idea that I'm trying to promote here tonight. Okay, this being said, yes, we want to talk about the nucleus. So if you go, again, we're now not going from the scales of the universe, but we start from matter. If you look deeper, you'll see atoms. If you look deeper, you will see a single atom with the electrons circulating around a nucleus. And in that nucleus, there is still more elementary particles. There are protons and neutrons, which in turn also have inside them the quarks. Now, for today, it's this collection of protons and neutrons that we're going to be talking about. And in fact, we can go now back all the way to Niels Bohr in 1937 and his student Kalkar, who proposed that you could learn a lot about the structure of nuclei by detecting the gamma rays that the nucleus might emit. And indeed, a good fraction of the picture we have today of what the structure of a nucleus is has emerged from this concept that by looking at the gamma rays, we can learn a lot about what's happening in this collection of protons and of neutrons. So let's just make sure that do a little refresher about nuclei and isotopes. For example, this is carbon-12 here. Carbon-12 will have 6 protons. That's what makes it carbon. And the positive charge of the protons is compensated, if you look at the atom as a whole, by the 6 electrons that orbit around it. And if this is carbon-12, then there will also be 6 neutrons. Now, that's one element of a large table of elements. And here they are all those that are known today. They're numbered by the number of protons that they contain. So hydrogen contains 1 proton, helium contains 2 protons, and so on. And in fact, these days, this table extends to an element with 118 protons. The fact we don't know where this periodic table actually ends, and there are still lots of efforts going on in laboratories across the world to try to see where in the table ends. Can we make an element with 119 protons or 120 protons and so on? In fact, there are even speculations that there is an island out there around 130 or even beyond. Now, very recently, this table, the Mendeleev table, as this is called, is about 150 years old now. In fact, it was 150 years old exactly last year. And over the last few years, we have been able to name some elements here that did no name yet, namely niobium, that's element 113, flerovium, element 114, moscovium, element 115, and livermorium as element 116. Then there is tennessine, and there is oganesson as element 118. Niobium, Japan is also as a second name, so to speak, and that comes from niobium. That's where niobium comes from. Flerovium and moscovium and oganesson, so are very Russian, and they are, because the 3 elements were actually discovered in a Russian laboratory in Dubna. This laboratory also was where experiments discovered livermorium and tennessine, but American groups played a major role in this. A group from Livermore National Laboratory and a group from Occasional National Laboratory, and that's recognized through these names. All right. If you have carbon-12, you have 6 protons, you have 6 neutrons. If I add a proton, I'll change the element. But if I add neutrons, I'm staying into carbon. For example, if I add 2 neutrons, I will have a somewhat larger nucleus, presumably, but the chemistry will not change. On the other hand, we would just have made carbon-14. And so for example, if you look in the periodic table, if you look at atomic number 4, you would be in beryllium, and there are several berylliums that can be made. Beryllium-9 would have 5 neutrons, is the stable one, but the beryllium-7, which only has 3 neutrons, you can make. It's not stable, but you can certainly synthesize it and it would live for a while. And the same thing is true for the ones with 6, 7, 8, and 10 neutrons. You notice beryllium-8 does not exist, but in fact, you can't make it. If you try to make it, it separates immediately into heliums, alpha particles. So our chart of nuclei, as we call it, this is the playground that the nuclear physicists will use, rather. The chart of nuclei will be a chart where on one axis here, we will have the number of protons, on the other axis, the number of neutrons. And so each isotope will be a little spot on this chart. And from what is known today is represented here. All these isotopes here that you see are the ones that are stable. In other words, you can go dig them out of the ground, you can find them in our atmosphere, things like that. But there are many more nuclei and isotopes known. And here they are. All the ones that are in this gray area here are nuclei that have been made, they have been synthesized. They probably occur, in fact, we know they occur in stars, but they are not stable, so they decay back to the stable ones. All the heavy ones that I just mentioned up here on the right, you see, are part of this collection. And one of the fundamental questions we have then is, well, how many protons can a nucleus hold? How many neutrons can a nucleus hold? And then there must be a limit to this table here. There must be a point where one cannot go beyond and the nucleus falls apart. On this side here, which I would say there are fewer neutrons, but we know pretty well, at least on a good fraction of it, where this line sits. We are very far away from knowing it on the neutron, on the side with more neutrons, which we call the neutron-rich side. So the message here already is that a large fraction of the landscape still remains unexplored, and the limits of existence are not known for most nuclei. We have about 260 stable ones. We have found about 3,000, but there are at least 4,000 more isotopes out there, and some of them are very important because they are made in stars, and that we are convinced of. So let's see how this table came about. The discovery is the first of the elements date back to 1890, and then you see as a function of time, you see little spots appear. All these here were discovered through radioactive decay. Then scientists started to develop a technique called mass spectrometry, and all the stable ones came about. And then accelerators came about and started synthesizing more and more elements through light particles first, then through fission, then through a process called fusion and spallation, and more recently by a process called fragmentation. I won't go into details of that, but that is how the table, the landscape we have today, was actually created. Okay, so this being said, let's stop this and move on. Discoveries have been made throughout the ages at different laboratories. For example, Berkeley is one of them in the United States that made a lot, but so did Argonne, so did Oak Ridge National Lab, for example. Others here, you will recognize the names. This is in France here, is Dubna that I talked about, and so on. Another way to look at this, and perhaps a better one, is here. Here is the number of nuclei that have been discovered as a function of time and also as a function of laboratory. Here is Cambridge. That is on a Stratford old laboratory. These are all done by basically decay, but certainly not with accelerators. The first accelerators were the cyclotrons, and this is where Berkeley played an important role. But you notice that the number of nuclei they synthesized went down, and this was taken over by a more powerful accelerator that had new capabilities from Dubna, which was in turn taken over by another one in Germany, in GSI. And the most recent of our tools to discover new isotopes is the one in green here. That's the accelerator at RIKEN in Japan. Now, it's been said that the contributions of the US have declined and that the Japanese, Russians, and Europeans have been on the rise. It's true, but it's about to change because by next year sometime, a new facility, the facility for rare isotope beams, will come online in the United States. It's currently being built on the campus of Michigan State University. It will be the most powerful accelerator for producing these new isotopes. And I could spend a full hour talking about that, but that will be for another day. Suffice it to say that it's going to be a factory of a lot of isotopes that we are dreaming of understanding, that we are dreaming of making, but that we have no way to make at the present day. So back here to the real questions. How many protons can a nucleus hold? How many neutrons can a nucleus hold? Those are questions that basically we need to answer if we want to understand the properties of the force that keeps the nuclei together, the strong force. And when we look at the isotopes, wherever we look, we find surprises, in particular on the more neutron-rich ones. And I'm just going to give you two examples here. For example, this is lithium-11. If I try to remove one neutron of lithium-11, it falls apart. The other neutron cannot be bound along to this lithium-9 that is here in the middle. It's like the Borromean rings from the Italian Borromean mathematician. If you disentangle the ring, one ring, if you break one ring, everything falls apart. That in itself is already sort of interesting, but then if you look here, here is an atom of one of the heaviest carbon isotopes known today, carbon-19, and that is the space it occupies. It turns out that surprisingly, the radius of this nucleus here is the same, roughly, than lead-208. So here is an atom, a nucleus, with only 6 protons taking as much space as another one with 82 protons in it. This is an aspect of the nuclear force we certainly did not anticipate. So we have a lot to learn about this strong force, one of the 4 forces, basic forces in the universe, the others being the electromagnetic one that binds the atoms, the weak force that is responsible for radioactive decay, and then of course the gravitational force that, for example, binds our solar system. So studying through gamma rays, so trying to understand how these nuclei are made, how they react, how the protons and neutrons inside them then react, is done in part by measuring gamma rays. And so the first thing we need to do is to excite the nucleus if we want to look at its decay back to rest by emitting gamma rays. So we need an accelerator for that. And here is an example of one. It's one that is at Argonne National Lab, and it's called ATLAS. You start from a source, you accelerate the beam through an accelerator, and then you shoot it straight on a target here. That is where the detector that I'm going to talk about now is, gamma sphere. And the gamma sphere is particularly good to measure the products of what we call fusion reactions. So imagine a beam accelerated to the accelerator, then one particle of this beam, it's a target nucleus. In about 10 to the minus 22 seconds, if you choose the energies properly here, the 2 nuclei will stick together and fuse into one another. Of course, if you bring the beam, you're going to bring in all the energy. Energy is conserved. Energy will be in the system, but also the momentum will be in the system. So the system is likely to rotate. But you make a nucleus, which we will call the compound nucleus. Since the energy that the beam brought is in here, this nucleus is very hot, and it can't basically stand it. So the first phase will then be to boil off literally particles. And it will mostly boil up neutrons, because if you have a charged particle, if you have a proton, you feel all the other protons inside the nucleus, and as a result, it becomes very difficult to escape. Neutrons are neutral, so they don't feel that force, they don't feel this Coulomb, force, and they can escape. But after a while, there isn't enough energy left after the neutrons have removed quite a bit of energy. And then the next step of the decay is where gamma rays occur. And it's actually, the process is not all that different from the one that you're all more familiar with, presumably, where an electron, when it cascades from one orbit around the nucleus to another one lower, will do so, and to preserve energy, it will emit an X-ray. It's the same thing that will happen here, except that the orbits we are talking about are inside the nucleus. They are what we call quantum states inside the nucleus, and when the nucleus goes from one state in excitation energy to another in low excitation energy, it will emit a gamma ray. So just like the X-rays, as Zach showed at the beginning, gamma rays are not visible to the eye. So we need a very high quality detector to actually measure the gamma rays, and that is where gamma sphere comes in. So I'm now going to first introduce gamma sphere by showing it to you through this little movie. After that, I will explain the principles of operation of the detector. Here we go.
This is gamma sphere, the most powerful detector of gamma rays in the world to date. Housed at Argonne National Laboratory, gamma sphere enables scientists to study properties of atomic nuclei. And here is how it works. Gamma sphere works together with the Argon Tandem Linac Accelerator System, or ATLAS. ATLAS can create a beam of ions from nearly any element, accelerate it, and throw it at nuclei to cause nuclear reactions inside gamma sphere. Think of ATLAS as a pitcher, and gamma sphere is a very good catcher. What gamma sphere is excellent at catching or detecting are the gamma rays emitted in a nuclear reaction. These rays are made up of light at frequencies that we cannot see, but gamma sphere can. By studying in great detail these rays of light, we hope to learn a lot more about the core of the atom and, for example, determine the shape of nuclei. So we have been playing a lot of nuclear catch. We used to think that all nuclei are spherical, like this baseball here. Play ball! But sometimes, when the gamma rays reveal the shape of the nucleus, it turns out to be a very different shape than we predicted. Atomic nuclei are full of surprises. When we start putting energy in the nucleus, it can start to rotate like this football when you throw it. Now, one question we may ask is, can the shape change? Sometimes the answer is yes. The shape can change, the nucleus stretches, or even snaps in two. That's nuclear fission. Tossing all this around is definitely fun, but it also teaches us about the nuclear force, and in addition, it has important applications. In medicine, 1/3 of all medical acts involve a radioisotope. This is truly the nucleus at work for our health. Detecting a tiny crack in an airplane wing can be done with gamma rays. The nucleus at work for our safety, or dating an historical artifact, or validating a work of art. The nucleus at work for our culture. What we are ultimately hoping to find is a theory that would accurately describe all nuclei, or the entire nuclear playing field. If we had this theory, it would allow us to understand, for example, what makes stars shine, and why some nuclei exist and some others don't. In other words, it helps us to understand the very stardust that makes up our world.
All right. Let me now continue by showing you some pictures of gamma sphere here. So here is the device, the way we would use it. When a reaction happened, the beam would come from the bottom here and the target would be in the middle of the apparatus. When we are working on it, of course, the apparatus would be open and you can actually see the target chamber. The beam travels through a high vacuum just to make sure, of course, that we keep all the energy and we focus the beam correctly on the target. Why is gamma sphere so good? The core of gamma sphere is up here on the left. It's a germanium detector. For all practical purposes, a germanium detector is a reservoir of electrons. And when a gamma ray comes in, it will knock some of these electrons and lose its energy by depositing it on the electrons. If all the energy is deposited in here, then because I forgot to tell you, we're going to put a bit of high voltage around this detector, the detector here, which means that as soon as an electron is knocked loose, because of the high voltage, it starts moving. And a charge, an electron in motion, is a current, and a current I can measure. So if all the gamma ray energy is deposited in here, I will get a very nice signal and actually a very accurately measured. Unfortunately, it turns out that a detector, the best detectors we have, do this about 20% of the time, no more. Because most of the time what's going to happen is a phenomenon called Compton scattering, where a gamma ray comes in, it will deposit some of its energy on the electrons here, but it will continue and escape. So the only way to get this 20% up is then by surrounding the detector from all sides, except where the gamma rays come in, by another detector. Not as good a quality detector, but sufficient to be able to tell electronically that the energy deposited here doesn't give you the correct signal, that in fact it is lying. So in other words, electronically, we would veto this here. Here is an example of that. This is a spectrum of a radioactive source of cobalt-60. Without this shield around, we would get these peaks extend a little higher here than what they show here, but we would get all this background here. If I turn this shield on, then we get the picture here at the bottom. So you see we've considerably reduced, sorry, I'll go back, the background, which means that if this source had emitted another much weaker gamma ray that would have been completely lost in this background, here, we may stand a much better chance to see it in the suppressed spectrum here. And that is exactly the principle on which a gamma sphere works. Now, here is another example of it. This here, germanium detectors have to operate cold at liquid nitrogen temperature. So you have a duo to do that. Here is the germanium. The pieces in gray here are the pieces of the scintillator. It's for the specialist, it's actually called the bismuth German that we do the suppression with. And all the rest, the only other thing to notice is that gamma rays can be emitted in all directions. And in nuclear reactions, you can emit as many as 30 or 40. So having many detectors around allows you not only to measure them all, but also to see in what sequence these gamma rays are emitted one after another. And that's how you end up with a system like this. Gamma sphere has 110 of these detectors. They're about 7 centimeters deep and 7.5 centimeters, 7 centimeters in diameter and 7.5 centimeters deep. And here are all the components. The scintillator, the germanium detector is right here that pick up gamma sphere. All right, so gamma sphere has other facets. I already alluded to this one. to this movie. Here is the real one, and here is the mock-up of Gamma Sphere that is on display at Universal Studios in Hollywood. We found it personally amazing that when they started reproducing Gamma Sphere, they even reproduced the colors of the devices the way we had painted them at the time. Why they did that, I have no idea, but that's the way it is. But some of you might be even more familiar with Gamma Sphere. Do you see Gamma Sphere on this picture? You know, of course, what the picture refers to, but Gamma Sphere is on the picture. Maybe a little hard to see, let me help you. It's right there. Indeed, that's what's there. That is a picture of a poster of a Gamma Sphere, which means that the producers of this program actually got a copy of a poster that we had made at the time to show at the Department of, in the hallways of the Department of Energy in Washington, D.C. And we made another copy of that poster actually for an exhibit for Congress. You see, even closer to today, Gamma Sphere has been popular. Now I just want to show you one example of the kind of signal that Gamma Sphere has given us. Here is one of these very heavy nuclei, nobelium-254. And you see, here is a spectrum of the gamma rays that the Gamma Sphere has detected. What you have here is increasing energy and number of counts. And you see this beautiful picket fence here of gamma rays. And that actually corresponds, it turns out, at the spinning of this nobelium nucleus. That's just one example. What I want to turn to now is to how can we use this also to understand better and to contribute to astrophysics. And when you look at stars, you're basically looking at extremes. For example, gravity here on Earth is 9.81 meters per second squared. That's the acceleration of gravity. In the stars, it's enormous compared to this, orders and orders of magnitude. The strongest magnetic field we have made on Earth so far is about 90 Tesla in a lab in Germany. Look at what pulsars can do. 10 to the 9, 10 to the 10, 10 to the 11 times more. And the same is true for accelerators. The cosmic accelerators are orders of magnitude, provide particles of in orders of magnitude larger in kinetic energy than our best accelerators on Earth today. In other words, you're going to see spectacular events in the skies. In 1987, this little spot here looked on the map of the sky, of the southern hemisphere, actually, totally anodyne. There was really nothing special happening until all of a sudden, boom. That's the explosion of the supernova 1987A. So supernovae are fantastic explosions. They radiate as much energy as the sun will emit over its entire lifetime. And it's a real explosion. That is, material is ejected at very high velocities. And the Crab Nebula that you already saw a picture of today is 6 light years across these days, but is the result of a supernova explosion. Now you could say, well, how many supernova explosions are there in the universe? And with our instruments, we have been trying to find them and to try to quantify this. And it looks like there is about one supernova, in other words, one of these explosions per galaxy per 100 years. So you'd say, well, that's not much. Why do we even worry? Well, if you realize how many galaxies there are in the universe, that means that a supernova explosion goes off about there are about 30 supernovae going off per second in the universe. So we have every reason to try to hope that one will happen, not too close to us, but close enough that we can observe it in more detail and try to understand better what's going on in the explosions. So what we know today is that in a supernova explosion, starting from elements like hydrogen, helium, and neutrons, nature will produce all the other chemical elements along the periodic table in nucleosynthesis by grabbing protons, by grabbing neutrons, by decaying to other nuclei that in turn can again grab protons and neutrons. And so to look a little bit better and try to understand better the mechanism, we need to find a recent supernova, not too far away from us. And there is one in Cassiopeia. It's in Cassiopeia. It's called Cas A, and it's sitting right here. And today, the light curve, because we understand the gamma rays, and we have detected the gamma rays, as I will show you, coming from this supernova remnant, we know that today that Cas A is dominated by the decay. The light curve is dominated by the decay of one specific nucleus, titanium-44. Now, this means that in this reaction, titanium-44 has been made from the elementary composition of protons, neutrons, and so on, to get over to here through a network of all kinds of reactions. And one of the last ones is definitely this one, where calcium-40 had been made, an alpha particle, or an helium-4, in other words, came along, and one made titanium-44. Now, titanium-44 made this way will decay. The half-life of titanium is 63 years. And so it will decay back to calcium-44. And it does so in this decay chain. 3 gamma rays occur at 68, 78, and 1.157 MeV. So 68, 78 keV, 1157 keV. And so that is the properties of these. Again, as has already also been talked about before, we have views of Cassiopeia A through X-ray, through optical, through radio, through infrared, and now also through gamma rays. And in fact, these 3 satellites, COMTEL, Integral, and NuSTAR, have been looking at Cas A. And here, for example, is the spectrum that COMTEL detected for this 1157 keV gamma ray, saying that titanium-54 is indeed giving a signal. And here from NuSTAR are the 2 other transitions, that's 68 and 78 keV. And we know that they are from titanium because we can actually measure the decay of the intensity with time, and it has the half-life of titanium-44. So this is Cas A, the way NuSTAR sees it, and this is what I'm going to be concluding with, actually, because there is a puzzle. Namely, here is the distribution, again, from pictures of gamma rays and X-rays like I just showed. Here is the distribution of hot iron in Cas A, and here is radioactive titanium. And you notice they're not quite the same. And in fact, calculations would have predicted that in this explosion, yes, you would have actually seen both going out just at about the same expansion rate in the same directions and so on. That is certainly not the case. So is the dynamics of the explosion wrong? Or could it be that somehow some of the iron has been masked by some other materials in the way? We don't know at the moment, but it is certainly an open question. It's just an illustration of how having these spectroscopic tools, these tools like gamma ray detection and so on, we can actually learn about that. That's the message I would like to leave you with, together, of course, with a few of the pictures of gamma sphere. As I said, it is still the most powerful spectrometer today, but we are developing the next one, which will be even more powerful, and which we'll need to exploit the radioactive beams that are come from our new facility in a few years. Thank you.
Well, thank you, Professor. That was an excellent talk. I think I can speak for everyone. I think we learned something and enjoyed it. And we actually already have a few questions that people have posted in the chat. So if you're ready, I think we can just jump in.
Please do.
So the first question we had is from Mark, who asked, what prevented a facility like FRIB at Michigan State being built prior to now?
Well, first of all, that's an excellent question. The answer is technology. What we were trying to build is basically a facility. The further you go from the valley of stability, the more difficult it is to make these nuclei, to make these isotopes we want to study. So we need a lot of beam intensity of particles per second to be able to make those. and developing the technology, the superconducting linear accelerator that can accelerate ions like uranium, like lead, and so on, to these very high energies we need to make these nuclei. That's what took the time, and that's why we were behind. Because the solutions chosen by the other people before us, like the Japanese, for example, involve cyclotrons, but cyclotrons cannot accelerate ions at the intensities comparable to what the linear accelerator can do. And that's why it took us a while to get FRIP going. But we're there now, or we're just about.
Awesome. We have another question, and Larissa asks, well, there's a few questions, so let me just read it. Why do you say the gamma sphere can create a beam of ions for most elements? Are there elements which react differently in response to gamma ray penetration, or do they all act similarly and predictably?
Okay, yeah, that's a complicated question. That's not a complicated. It's an interesting question. But let's first correct something. The beam, to make the nuclei that we're going to study the gamma rays from, we need particles. That's done with charged particles from the accelerator. But now we look at the gamma rays coming down. It turns out that not all nuclei behave the same way. In other words, depending on the number of protons and the number of neutrons that you would have in a nucleus, the behavior of the nucleus can be very different. And yes, we all, as I said in that little video, we already thought that all nuclei would be spherical, but it turns out that's more the exception than the rule. Most of them are actually deformed slightly and closer to an American football or to a doorknob, like the Earth. You know, the Earth is slightly oblate, pushed on the tip, so to speak. Same thing with some of the nuclei. But even more impressive is that we have now found nuclei where that might be spherical near the ground state, but you pump a little bit of energy in it through a nuclear reaction, and they deform. And then, yes, indeed, sometimes they split, sometimes they don't. And in fact, we have now found nuclei where three shapes can happen: a spherical ground state, a doorknob type state, and then a little higher in excitation energy, a prolate state. And that is all due to the way the protons and the neutrons rearrange themselves in the nucleus, and what the forces, the nature of the forces between them. And that is where we have a lot of surprises yet. We thought we had some of it under control, but until recently we couldn't look at nuclei with many neutrons. And it turns out that they are very different beasts. So there are aspects of the nuclear force that we didn't really know well until now, and that we're only now discovering. Zach, I can't hear you.
Sorry about that. So we have the next question from Ethan. And Ethan asked a question about the detections. So how can you ensure that the rays in the gamma sphere detectors are gamma rays and not X-rays or some other high energy radiation?
That's a very good question, Ethan. The reason I don't see the very low energy X-rays is a very pedestrian one. You notice the germanium is encapsulated in an end cap because we need to keep it cold and in vacuum. That end cap will stop the X-rays, and so that's the reason. For very high energy particles, charged particles, and so on, actually charged particles will also mostly be stopped in the end cap, but neutrons can't get in, and in fact it's a problem for us. Because when the neutron gets in a germanium detector, it will dislodge some of the germanium atoms themselves. And in fact, that means that the detector deteriorates with time. Fortunately, we have a recipe for that. We bring the detector back to room temperature and even heat it up slightly so that we shake the crystal back into its original form, where all the germaniums are back in place. Then we cool it down again and we go again. And then for very high particles like Cosmic rays and so on, they're always a problem. Fortunately, and there is very little we can do about it, except that the scintillators that sit around here, the germaniums, of course, shield the germanium to some extent too, so we don't see too much of them. But a germanium detector without background does not exist.
Thank you for clarifying that. We actually don't have any more questions in the chat, but I think I mentioned there's a little bit of delay between
Yes,
when we
sure.
read them. So we can give a little bit more and see if anyone writes any.
Absolutely.
I have one actually in the meantime.
Yeah.
And this stems from having forgotten, I think, my chemistry and all that good stuff. But when you were showing the periodic table, you were showing the new heavier elements that have been discovered. I think the heaviest one was atomic
118.
number 118.
Yep.
So 118 on the far right, does that still follow the noble gas? It's one of the noble gases and all those other kind of trends.
That's a great question, and it's a question of much debated. And the reason it's debated is that as you go to these higher mass nuclei, if you look at the outer electrons, and some of the electrons anyway of these atoms are now becoming relativistic, and that means that it's much more difficult actually to calculate the exact structure. We are speculating that they look like in the rows they have been put in, but the chemistry has not been done very well yet. And the reason is that I think that the world supply of element 118 so far is something like 30 or 40 nuclei. So we haven't had the opportunity to do the chemistry yet. We are starting to do the chemistry on element 112 and element 113 and see whether they sit in the category in terms of chemistry. And in some aspects, apparently they do. In some aspects, the jury is still out. So yeah, we may have to modify the table. It may not look as pretty as it looks now.
That's very interesting. Thank you for answering that. And I think it doesn't look like we have any more questions coming in on the chat, so I think we can go ahead and close it up.
Okay.
Thanks everybody for coming, and thank you, Professor Jannsens, for giving this great talk. And remember, our next event will be in February. So thanks for coming, and we'll see you all there. Bye-bye.
Okay, have a good evening.